Hello everybody and welcome to the sixth and final video in this blockchain for beginners tutorial series. In this video, I'm going to talk to you about Ethereum scaling solutions, specifically solutions on layer 1 and on layer 2. And of course, I'll describe what layer 1 and layer 2 mean. Now, the reason we need Ethereum scaling solutions is because, as you've seen through this series, Ethereum can be quite slow, and the number of transactions that it can handle per second is very, very small. Now, this means it takes a really long time for us to actually submit a transaction to the blockchain and have that processed and validated. And if we want to be using a smart contract to perform computations, that can take a really long time as well, or be infeasible based on the amount of, say, iterations we need to do within a for loop or something along those lines. So there's tons of reasons why we need better scalability on Ethereum, and fortunately there's many different solutions. So with that said, we'll go ahead and get into the video, but I do want to thank Cartesi for sponsoring this video and this series. They're an awesome company that have been helping me come up with all of the content for this series, and they're actually working on a bunch of layer 2 blockchain solutions right now and trying to make the blockchain more accessible and scalable for developers. So definitely check them out from the link in the description. They have a ton of detailed articles on a lot of the stuff I'm going to go over in this video, and I do just want to quickly mention here in the intro that this is going to be very high level. I'm not going to get into a ton of technical explanations about these different solutions. I just want to give you an introduction to them and then encourage you to research and learn more. Anyways, let's start talking about the difference between layer 1 and layer 2 solutions. So in blockchain world and in this video, you're going to see the terms layer 1 and layer 2 a lot. Now, layer 1 is referring to the blockchain network itself, so the actual Ethereum main network, and layer 2 is referring to stuff built on top of that network. So when we talk about increasing the scalability of Ethereum, when we're referring to layer 1, we're talking about actually modifying the underlying blockchain technology, so changing the architecture, increasing the block size, decreasing the block size. Whatever the solution is going to be, it's going to be right on Ethereum, and that's something that we can't really directly modify ourselves. The people that are working on Ethereum would have to actually change. Then we have layer 2. Layer 2 is referring to solutions we build on top of the blockchain. So we're not touching layer 1. We're not modifying the Ethereum network. We're doing stuff on top of this to increase the scalability. So of course, I'll get into those different solutions. But again, on layer 2, we're relying on layer 1 to give us the security and aspects of the blockchain, but we're not actually going to be modifying that underlying technology and that underlying architecture. Hopefully that is clear. Now what I want to do is talk to you about something known as the Scalability Trilemma, which has to do with the different aspects of a blockchain that we want to have and that we need to consider when we're picking different blockchain solutions. So the Scalability Trilemma is essentially a triangle. I'll put a photo up on the screen where each vertex or point is one of the properties or aspects of a blockchain that we'd like to have. So here we have security, decentralization, and scalability. Now, broadly speaking, what this says is that whenever we implement a solution, we end up lacking in one of the areas of this triangle, so one of these points. For example, if we implement a solution that has great security and great decentralization, typically we're going to have worse scalability. Where if we implement something with great scalability and great security, we may have worse decentralization. Now, this is not always the case. There is some solutions that are great in all three of these areas, but this is something that we want to think about when we're actually talking about different blockchain solutions. So does this increase decentralization? Does it decrease decentralization? What are the pros and the cons and the trade-offs as it relates to the scalability trilemma? Now, before we go any further, I do really want to define scalability as well as security and decentralization just to make sure we know those terms. So when we're talking about scalability, the common thing to refer to as it relates to blockchains is transactions per second or transaction throughput. Now, that is one of the areas of scalability that we're concerned with, but we're also concerned with data scalability as well as computation scalability. So when we were building smart contracts, one of the big issues there was we don't want to store a ton of data and we can't do too many computations in the smart contract because of the cost on the Ethereum network and the time it takes to actually process those. So keep that in mind as we go through this video. It's not just the number of transactions, it's also computations and data on the blockchain. Now, as we go to decentralization, that's really referring to the centralization of power, or in this case, the lack of centralization of power. So the example I always like to use is a bank. A bank is an example of a central institution or organization. They have, a few executives or a few board members that really control what the bank can do. They have investors, they have government interests, whatever. It's very, very centralized. The people that use a bank don't control what the bank is able to do and what control they have of your money. It's the bank itself, very central, that controls all of that. So hopefully that makes a bit of sense. Now, when we talk about blockchain, we want everything to be decentralized. So there's not one person, one institution, or maybe a few people or few institutions that have control over the network. Ideally, we want millions of computers or thousands of computers around the world to be running and securing this network so we're less prone to hacks, less prone to corruption, and all of those other things that can happen when you have central power and central, authority of something. So hopefully that makes a little bit of sense. Then we're talking about security. This is pretty straightforward, but how secure is the network? How easy is it to be hacked? How sure can we be that this transaction is valid when it's posted on the blockchain ledger? All of those types of things relate to security. All right, so that is the scalability trilemma. Keep this in mind as we go through the rest of this video. Now I'm going to start talking to you about layer 1 solutions. Now I'm not going to spend too much time here because we don't have much control over layer 1 solutions. We can't really build a layer 1 solution because we don't have control of the Ethereum network. Regardless, though, I will talk about why we would want a layer 1 solution. So why would we actually want to improve Ethereum? Well, as I'm sure many of you are aware, Ethereum is relatively slow. So when we're talking about scalability, it only does about 15 transactions per second. And in contrast to something like Visa that can do upwards of about 60,000, that's really, really slow. And that makes it infeasible for a ton of different applications, especially something like being the global currency, right? If we wanted everyone to be using Ethereum for their day-to-day transactions, well, that would take a really long time because we would have to be waiting hours, maybe even days for a transaction to go through because we can only do 15 per second. Now, in terms of computations as well, we've seen when we were working with smart contracts, we're really limited in what computations we can do. We probably can't implement any advanced data structures and algorithms, we can't store too much information, and we can't do too many iterations without it costing us a ton of money on the blockchain. So that is kind of the reason we would want to improve Ethereum because of those lack of scalability issues. Now, Ethereum is very decentralized and is very secure, so we're not super concerned with those two aspects. We just really want the scalability to increase without hurting the decentralization and hurting the security. Anyways, let's talk about the layer 1 solutions. So currently, Ethereum is actually working on a layer 1 solution, which they're calling Ethereum 2.0. This is going to be a complete change to the architecture and the algorithm used for Ethereum. So I'm sure many of you have heard of this before. They've been working on it for a really long time, and it should be out relatively soon, but they're going to be changing from proof of work to proof of stake. Now, I'm not going to discuss the differences here or get into kind of a debate about which is better, but that is what they're doing. They're changing the main algorithm from proof of work to proof of stake, and ideally, they're going to be bringing the transaction throughput from about 15 transactions per second to upwards of 100,000 transactions per second. Now, I cannot confirm this. These are just the rumors and what I've heard online and seen when looking at the project. Anyways, that is kind of what they're doing. Now, in Ethereum 2.0, they're doing a few other things. One of the main things that they're adding is something called sharding. So sharding is really this process of taking a large piece of data and splitting it horizontally into smaller pieces of data, which can be handled by multiple computers at the exact same time. So to put this simply, imagine I have one piece of data, and this piece of data can only be processed by one computer at a time. Well, it's going to be slower to process that data than if I split this data into, say, 64 chunks or 120 chunks or whatever the number of chunks is going to be, and allow 120 computers, 2,000 computers, whatever the number is, to process these smaller pieces of data at the exact same time. So that's exactly what Ethereum is aiming to do. Take the large piece of data, split it into multiple smaller pieces of data, and then allow for parallel processing and to drastically increase the number of transactions per second. In fact, this is a similar thing that many large companies do and many large databases do to increase the efficiency or increase the scalability of their systems. So this is not just something that's done in blockchain. This is done generally in computer science, and I would encourage you to read more about it and look it up if you're interested in exactly how sharding works. So with that said, that's going to wrap up our layer 1 solutions. Now I'm going to talk about the layer 2 solutions. So as a reminder, layer 2 solutions are simply solutions built on top of Ethereum. So they rely on the Ethereum network and they do not modify it, and they aim to increase the scalability while again still keeping the decentralization and security aspect. So with that said, let's talk about some different layer 2 solutions. Now the solutions that we have are things like state channels, sidechains, and then rollups. Now I'm actually going to start with sidechains, so I probably should have listed it in the other order. But what a sidechain is essentially another blockchain network that has a different architecture than the Ethereum network and makes it better for scalability. So what a sidechain actually does is it links to the Ethereum main network and makes it very easy to transfer assets between the two different chains. Now, typically sidechains are going to be much smaller, they're going to have less validators, they may have smaller block sizes, and this does actually decrease the security and the decentralization of the sidechain, but it drastically increases the scalability because now, rather than me sending a transaction to Ethereum, I'm going to send it to a sidechain, and then the sidechain can kind of link up with the Ethereum main network and allow me to transfer the assets between the two networks very, very quickly, or very easily at minimum. So an example of a sidechain would be something like Polygon. I'll put up an image on the screen. These are controversial, and there's a lot of reasons why you may not want to use a sidechain. But again, the basic reasoning here is rather than using the Ethereum network, we're going to use a completely, entirely different blockchain network that's going to be somewhat linked to the Ethereum main network, which allows us to take the smart contracts running on the sidechain and very easily port them over to the Ethereum main network while still maintaining all of the data, all of the assets, and all of the information essentially that was posted to the sidechain network. Hopefully that makes a bit of sense, but those are sidechains. So the next solution that I'm going to introduce to you is something known as state channels. Now, I just want to emphasize before doing that, again, I'm bringing this to you at a very, very high level. There's a lot of details and nuance with all of these solutions, and you really should do some research and look at these more before actually trying to implement them or use them for your decentralized applications. So please keep that in mind. This is a very, very general introduction. Anyways, state channels. To explain the usefulness of state channels, I want to introduce to you a problem of making a decentralized application. So if we wanted to make a decentralized app, we want this to be some type of game, maybe a game like chess, right? Well, this game requires many state changes. Now, we know when we make a decentralized application, we're going to have a smart contract. The smart contract handles the state of our application. If we're talking about chess, it would need to store the state of the board. So if we want to play a game of chess on the Ethereum network, what we would have to do is send transactions to the smart contract to update the state after every single move was played. Now, at least in the chess games that I play, they're like 5 minutes long or 3 minutes long, and we make moves every few seconds, right? So I make a move, my opponent makes a move, and every time that would happen, if we were running this on Ethereum, we would need to submit a transaction to the network. However, the next player can't make a move until that transaction is verified and the state has been updated in the smart contract. And we know that that can take a really long time to happen, so that makes it infeasible for us to play a game that has very rapid state changes. Hopefully that makes sense, but you would be sitting there waiting 30 minutes, an hour for the transaction to be finalized before the next player would be able to move, and well, that completely defeats the purpose of like a quick game of chess or something along those lines. So this is where we introduce state channels. So the idea here between state channels is that if we have a ton of microtransactions or many transactions that are going to be occurring in a short period of time, rather than doing them on the blockchain, we're going to take them off the blockchain and do them in a secure way that can later be verified by the blockchain. So a state channel is essentially a communication channel, a peer-to-peer messaging channel, where me and someone else who are participating in, for example, some type of game, are going to be sending signed messages to and from each other with the state of the game. So if we're playing a game of chess, I'm going to be sending a message that's signed by me to my opponent saying, I made this move. And then they're going to send me a message that's signed and said, I made this move. And we're both going to be verifying that the state is correct at each point in time by signing these messages. Hopefully that makes a bit of sense. Now, the way that this works is we're first going to send a transaction to a smart contract sitting on layer 1 to open up the state channel. Once the state channel has been opened, we're going to do all of our transactions, the micro quick ones, off the blockchain. They will happen almost instantly. Then at the end of the game, we're going to send one transaction to the smart contract with the final state. And we're going to say, hey, we finished the game. And then the smart contract is essentially going to verify that the state is correct. And there's a lot of stuff that goes on to do that. I won't really talk about how that works. And if we were playing for, say, 1 Ethereum, so whoever wins the chess game gets 1 Ethereum, then that Ethereum would be transferred, and we would have had to kind of stake that at the beginning of the game. So hopefully that makes a bit of sense, but typically state channels allow for us to have very fast transactions. They make it very cheap because we don't have to pay gas fees when we're doing this off the blockchain. We just have that first and last transaction that require the gas fee to open the state channel and to close the state channel. And typically they do allow for the same security and decentralization. However, you may have the security be slightly decreased depending on the way that you're verifying the states and what you're doing between the blockchain and the off-chain, or between layer 1 and layer 2. Again, I don't want to get into this too much. Those are state channels, very useful when you have a ton of microtransactions that need to be performed very, very quickly. So now we are moving on to the final solution I have in this video, which is rollups. Now, before I get into those, I do want to mention that Cartesi actually implements a ton of layer 2 solutions and makes it really easy for developers like yourself to use these solutions without having a full understanding of how they work and what's going on behind the scenes. Cartesi is working on operating systems, libraries, modules, packages, frameworks, all of the stuff you could imagine that's going to make it easier for you as a developer to use these types of solutions that are really complicated on a lower level. So make sure you check them out from the link in the description. Anyways, let me talk about rollups here, and I will also mention that Cartesi has a ton of articles that explain this stuff more in depth. If you're interested, again, reference them from the link in the description. So a rollup is essentially an idea that we're going to take all of the transaction execution, so the computations associated with the transaction, and perform those off the blockchain while posting transaction data to the blockchain on layer 1. So the basic concept behind rollups is that it's very expensive to perform computations on the blockchain. It can also be very time consuming. So rather than do them on the blockchain, let's perform our transaction execution off of the blockchain and then post the transaction data to layer 1 and have a smart contract on layer 1, so on the blockchain, that can validate that the execution that we did off the blockchain was indeed correct. Now, I know that's confusing, but essentially we're taking the time-consuming operations and computations, performing them off the blockchain, and then posting all of the data to the blockchain, where we can then validate that it is correct, and we can use the properties of the blockchain to store the data. Now, another advantage of the rollups is that what they can do is they can bundle multiple transactions, so maybe hundreds or thousands of transactions, into one smaller transaction, and then post that to layer 1. So rather than having the user have to send 1,000 transactions directly to a smart contract, which costs a lot, takes a lot of time, we're going to send it to whatever's rolling up these transactions. It's going to kind of bundle them all together and then send one transaction to the blockchain that contains all of the data that it needs, or the state change that's going to be made. So before I can go any further, because I do want to give you some more detail here, I will mention that there's some different types of rollups. So we have optimistic rollups and pessimistic rollups. Now I'm going to start with optimistic rollups. Now I do want to add here that the blockchain community currently considers rollups to be one of the most promising solutions for scaling Ethereum, and the reason for that is that they allow you to scale the computations and throughput of the network without compromising on security and decentralization. So using that in combination with sharding, which allows you to scale the data on the network, really gives you the best of both worlds and allows you to scale Ethereum in all three of the areas that we talked about. So sharding scales the data, and the rollups allow us to scale the computations as well as the throughput, so the transactions per second. So you're likely going to be hearing a lot more about rollups in the future, and maybe even using them yourself. And if you were to pay attention to any of the solutions in this video, this would be the one that I recommend. So when we talk about optimistic rollups, what we're really referring to is that the smart contract that's sitting on layer 1 is assuming that any of the transactions sent to it are valid. So any of the state changes that are made, any of the transaction data, we just assume that's valid and that it's not malicious. Now, this allows for us to have very quick transactions and to perform faster computations off the blockchain because we don't have to prove that everything is correct. However, this does mean that someone could submit a malicious transaction. Now, there is incentives put in place to make sure that people do not submit malicious transactions. For example, there may be something like staking Ethereum. So whenever people are dealing with rollups, you may have to stake some Ethereum that says, hey, I'm going to be a good actor. I'm not going to submit any malicious transactions or state data. And if you do that, so if you are malicious, your stake could get slashed. That could be the incentive or de-incentive from performing poorly or having bad behavior on the network. Hopefully that makes a bit of sense. But the idea here is that we're assuming everything is correct. Now, if someone does do something that is not correct or is invalid or malicious or whatever, anyone can submit something known as a fraud proof. Now, this fraud proof essentially says, I believe that this state is incorrect. I believe that someone did something malicious. Go and verify that it's not, or go and verify that they did indeed do something malicious. So that's what it's called. It's a fraud proof. This puts the smart contract into a specific mode where it's going to go and validate that all of the transactions and data that are sent is actually correct. And if they are not correct, it's going to punish whoever submitted the incorrect transaction. Hopefully that makes a bit of sense, but that is optimistic rollups. Again, just really think about the fact that an optimistic rollup is assuming everything is correct, and it's only doing a validation if someone submits a fraud proof. All right, moving on now to pessimistic rollups. Now, pessimistic rollups are kind of the opposite of optimistic rollups. In a pessimistic rollup, you cannot submit or update the state of a smart contract unless you submit something known as a validity proof. Now, this proof is a specific cryptographic proof. I'm not going to really talk about exactly how it works, but essentially off the blockchain, when you're performing all of your computations, you also need to compute this proof, and then this proof is sent to the smart contract. And you can only submit or update the state, of the smart contract if you have this proof alongside it. Now, the only real issue with these type of proofs, though, is that they can be inviolable to compute for really complex transactions. So these are time consuming and difficult for a computer to come up with, these cryptographic proofs. And so if you're doing anything that's too complex, it can be inviolable to come up with one of these proofs. And in that situation, you need to use an optimistic rollup. Now, the reason you would use one of these proofs, though, is because this limits the amount of data that the smart contract needs to hold, because all it needs to do is hold a state, because it can only update the state if it has a valid proof. I understand it's a little bit confusing, but in the optimistic rollup scenario, it's holding all of the transaction data, and it's only doing a verification when a fraud proof is sent. So it is time consuming when you send the fraud proof, but ideally you're not having that happen very often. Whereas in a pessimistic scenario here, the smart contract is holding much less data. It's just storing the state, and it's only updating that state when you submit the proof. This means it's really easy for the smart contract to validate that everything is correct. However, it takes more time off the blockchain to be able to submit these state changes because you need to perform this validity proof, and sometimes this validity proof can be inviolable to compute. All right, so that's pretty much all I can share with you related to rollups, without getting into too much detail. Again, I want to emphasize this at a very high level. There's a ton of stuff that I skipped over and omitted in this video. With that said, I'm going to start wrapping it up here. Another massive thank you to Cartesi for sponsoring this video and this series. Make sure you check them out from the link in the description. They have all kinds of articles, very smart people there that are implementing these types of layer 2 solutions and are trying to make it much easier for you and me to develop decentralized applications without the huge issues or limitations of Ethereum that we looked at in some previous videos. I hope you guys enjoyed this series. If you did, make sure you leave a like, subscribe to the channel. Please leave a comment down below and let me know if you want to see more blockchain on this channel, because I'm hoping to do some more series in the future. And with that said, I will see you in another YouTube video.